Okay, let's unpack this. We've got a great stack of sources here, and they're all focused on cost accounting, specifically how managers, make decisions.
Right.
But sometimes when you're that deep in the numbers, you really need a shortcut, a way to see the big picture.
And that shortcut is precisely what we're diving into today. It's called the Scattergraph Method.
The Scattergraph method.
It's basically the ultimate visual tool for solving what can be a persistent headache for managers, which is the mixed cost problem.
Right, and by mixed costs, we're talking about those expenses that are just tricky. They don't fit neatly into a box.
Exactly. Think about your electricity bill.
Sure.
It's not purely fixed because, I mean, the more you produce, the higher it goes, but it's not purely variable either.
Because there's always that baseline amount you pay just for being connected to the grid.
That's it. And that mixed behavior can be a huge budgeting trap.
It seems like it.
It is. If you can't accurately separate that total cost into, its fixed part and its variable part, your budgets are basically built on sand.
So managers need to know, like, if we ramp up production by 30%, what does that actually do to our costs?
Precisely. And the scatter graph is the fastest way to get a really solid, functional answer to that question.
So our mission for this deep dive is to take historical data. In this case, we have monthly labor hours and electricity bills, and turn all those numbers into one single predictive equation.
Yeah, we're basically turning chaos into clarity. The foundational rule of this whole approach is its visual power. It takes a bunch of confusing data points and forces a line, a pattern, out of them.
It makes the cost behavior visible.
Instantly visible.
Okay, but before we even get to interpreting it, the setup itself has a golden rule, right? You can't mess this part up.
You really can't. This step is absolutely fundamental. You have to assign the right variables to the right axis.
The vertical axis, the y-axis, that has to be cost, right?
Yeah.
In dollars.
Always. That's your dependent variable. It's the thing you're trying to predict.
And the horizontal one, the x-axis, that's your activity level.
That's your cost driver, the independent variable. In the example from our sources, that's direct labor hours.
So just to be clear, what you're doing is you're visually saying that the cost depends on the activity.
That's the relationship we're testing. Then you just take your data, here we have 6 months of observations, and plot each one.
Like for month 1, you go over to 6,000 direct labor hours and up to a $60,000 electricity cost, and you make a dot.
And you do that for all 6 points.
And the cool thing is, the moment you're done plotting, you already know something.
You get instantaneous feedback. Once those 6 dots are on the graph, you can see the trend.
In this case, the points all trend upwards. More hours, more cost.
Which confirms it's a mixed cost. If they were, just clustered in a flat line, it would be a purely fixed cost.
So that first visual check is actually a huge win. You know right away if your basic assumption about the cost is even correct.
Absolutely. It's your first layer of validation. But the real work, the art of it, begins with the next step.
Drawing the line.
Drawing the line.
And this is where we move from, let's say, objective plotting to something more subjective.
It is. You're visually fitting a straight line. People call it a regression line or a best fit line right through the middle of that cloud of points.
And the goal is what? To just kind of eyeball the average?
You're trying to minimize the total distance from all the points to your line. You want, roughly half the points above it and half below it.
Okay, but hang on a second. This is where I get a little nervous. If we're relying on someone just visually estimating a line, isn't that a little dangerous for big budget decisions?
That is the core trade-off.
Yeah.
And it's something you have to embrace with this method. It is subjective.
So if I asked 3 different accountants to draw this line,
You might get 3 slightly different lines. Yes. The sources even mention this. An analyst might see 3 points sitting a bit higher and be tempted to nudge the line up a little.
and that tiny nudge would change the final numbers.
It would. It would change the fixed and variable cost estimates.
So why on earth would we use this instead of a proper statistical tool, like a least squares regression that a computer can do perfectly?
Time and practicality. This is the quick and dirty approach.
Ah,
If you're in a meeting and you need a cost estimate in the next 5 minutes, you're not going to run a statistical analysis. You grab a pencil and draw the line. Least squares is mathematically perfect, yes, but sometimes that precision doesn't actually lead to a better decision, just a slower one.
that's a really interesting distinction. We're trading perfect accuracy for immediate actionability.
Precisely. This is a screening tool, not an audit tool.
Yeah.
Once that subjective line is on the paper, you actually turn your back on the original data points.
Really? You just ignore them.
For now, yes. You focus only on the properties of the straight line you just created. That line is what holds the answers.
Okay, so let's pull those answers out of the line. First up is the fixed cost. How do we find that?
That's the Y-intercept. You just trace your line all the way back to the vertical axis, back to the point where the activity, the labor hours, is 0.
And whatever dollar value it hits, that's your fixed cost.
In the example, our line crosses the Y-axis at $40,000.
And that $40,000 is a powerful number, isn't it? It's telling you the cost of just having the capacity to produce.
Exactly. It's the cost to keep the factory minimally lit and connected, even if it sits completely idle for a month.
So if you shut down production tomorrow, your electricity bill doesn't go to 0.
It drops to that baseline of $40,000.
Mm-hmm.
And knowing that is critical for all sorts of decisions.
Okay, that's one piece of the puzzle. What about the other part, the variable cost per unit?
For that, we need the slope of the line.
Right, rise over run. The change in cost divided by the change in activity.
And this is key. You pick 2 points on the line you drew, not 2 of the original data points.
I see. Because we're analyzing the line, not the messy data.
Exactly. So using the estimate from the source, we can see the line goes from that intercept $40,000 at 0 hours up to a point where the cost is, say, $70,000.
Okay, so the rise is the difference. $70,000 minus $40,000 is $30,000.
And that $30,000 rise in cost happened over a run of 7,000 labor hours.
So we divide the $30,000 rise by the 7,000-hour run.
And you get your variable rate. It comes out to $4.29 per direct labor hour.
And that $4.29, that's the magic number for a manager. It means for every single extra hour of labor you use, your electricity bill goes up by exactly $4.29.
It gives you that marginal cost. It's why separating these costs is so fundamental to good decision-making.
So now we have the two pieces. We have the $40,000 fixed cost and the $4.29 variable rate.
And now we put them together into the final deliverable, the predictive cost equation.
Which is total cost equals the fixed cost.
Plus the variable cost per unit multiplied by your activity level.
So for us, it's total cost equals $40,000 plus $4.29 direct labor hours.
And there you have it. You've taken 6 random-looking data points and boiled them down into a simple formula that can predict the future, within reason, of course.
Right. And this is where it gets really useful for a manager. Let's say you're budgeting for a really busy month, maybe 10,000 direct labor hours, a number you've never actually hit before.
No problem at all. You just plug 10,000 into the equation. The fixed cost is still $40,000.
And the variable part is $4.29 times 10,000, which is $42,900.
Add them together.
And you get a predicted total cost of $82,900. That gives a budget manager a real number to work with, instead of just guessing.
And it's very reliable for what we call interpolation predicting costs inside the range of activity you've already seen.
But you have to be careful about extrapolation, right? Predicting way outside that range.
Oh, extremely careful. That formula might not hold if you tried to predict the cost for, say, 50,000 labor hours. At that point, your whole cost structure might change.
You might need a bigger facility or new equipment, which would jump up your fixed costs.
Precisely. The assumption of a straight line only holds true within what we call the relevant range.
But the real strategic payoff here isn't just about the electricity budget, is it? It's about how this links to bigger things.
It's the absolute foundation for what's called cost volume profit analysis, or CVP.
CVP, this is where you connect costs to revenue and, well, profit.
Yes. Once you know your fixed baseline and your variable rate, you can start asking the really important strategic questions.
Like, how many units do we have to sell just to break even?
Exactly. Or, how much can our sales drop before we start losing money? That's your margin of safety. It even gets into more advanced ideas like operating leverage.
And it all starts with this simple visual method of splitting the costs.
It's the gateway. It lets you predict costs for new products, evaluate outsourcing deals, set prices. It all flows from this one simple separation.
Let's circle back to the visual part for a second, though. What if you're plotting your points and one of them is a huge outlier, like way off the line you want to draw?
That's actually another one of its hidden strengths. Visual anomaly spotting.
So an outlier isn't just noise, it's a signal.
It's a big red flag. That point is screaming, investigate me. It could be a billing error, a machine breakdown, some major inefficiency that month. The line shows you what the cost should have been, and the point shows you what it was.
Whereas a purely mathematical analysis might just average it out and you'd miss the insight.
It could smooth it over, yes. The scattergraph forces you to look at it and ask why.
So, to sum it up for someone wanting to use this, when is it the right tool for the job.
Use it for quick estimates, for preliminary analysis, for spotting trends and outliers in a small set of data. It's for getting a rapid intuition about how your costs behave.
And when should you absolutely not use it?
When the stakes are critically high, when a decision is irreversible and involves huge sums of money, or when you have hundreds of data points, then you need the statistical precision of a proper regression analysis. This is not for that.
So it democratizes cost analysis. It makes an abstract concept feel tangible.
That's a great way to put it. It turns confusion into clarity. And that ability to confidently split your fixed costs from your variable costs, that's really the key to proactive financial control.
And that control is what drives profitability.
At the end of the day, yes.
So what does this all mean? The Scattergraph method, it seems to me, perfectly captures this business dilemma of balancing accuracy with practicality. It's the definition of actionable insight.
It is.
And since success in management often hinges on speed more than it does on statistical perfection, you have to ask yourself, how much speed is worth accepting the subjectivity of just eyeballing a line? And on the flip side, when you demand that perfect, absolute precision, what is the practical cost in time, in resources, in missed opportunities of waiting for that perfect analysis? It's a trade-off that really defines the pace of modern business.